All right. So let's just start. So we're going to start with modeling overview. And previously we have talked about that there are technically two versions or two view exists. One is that model-centric view, and the other one is data-centric view. And I say that basically in model-centric view, your focus is iterating on the model constantly, which is something that happens in the basically academy mainly. And data-centric is kind of like focused on improving the data over and over, right? And the whole idea is that there are some challenges in it doesn't matter either way, but the challenge is that your AI system is code and your data at the same time. We have talked about this enough up to this point. The entire MLOPs is iterative. Doesn't matter if it's a cycle of data, cycle of model, cycle of evaluation. It's always a cycle. And what some of the challenges that you're going to deal with is that, and it's like the first one is the main one, doing well on your training data, doing well on your data doesn't necessarily mean that you're doing well. Okay, that's really important to remember. Even doing well on your dev and test data doesn't necessarily mean you're doing well on the business metrics. Okay, because you could just have the data that you have is always a batch, right? There's a sample, a snapshot of the data. You could do really good on training, validation, testing, but when as soon as it comes to real business metrics, and it's like it doesn't work. Okay, so there are reason for those, but let's just start with this. Like, why low average test error isn't good enough? So let's think about the search. When you do search, there are technically two types of search: informational or transactional or navigational queries, right? So what does that mean? If you want a recipe, you go on Google and you basically search, right? And what you get is not the best result, it's just a recipe, right? However, if you want a best answer for your basically search, you basically do navigational query like a Stanford, Reddit, YouTube. They give you the best match, right? I know this says they're like a there's some. What's the other company? Sis? You guys using it for search, AI search?
Atlas.
Perplexity, right? So they will come to the navigational queries, right? Because the motto is that to give you the best answer, ad free. Now they have added some ads to it. So, the other thing is that we were talking about why having a good test result is not good, is not enough. The main reason could be that you need to be sure that your model does not basically discriminate or basically doesn't generate basically unequal results based on ethnicity, gender, location, language, and any protected information basically. If your model generates a different result based on protected information, by law, you basically cannot use that model because it's by law you can get sued. You know, it's kind of like a something to keep in mind. For example, another thing is that product recommendation. And again, this I have said that so many times, and Google lost a couple of lawsuits on this in a couple of billions basically to Europe, the European nation. And again, what was the reason was that the search engine was every time you do a search in Europe for a certain product, it was by default always basically recommending top US companies as first result of the search, then going to a smaller European companies. So they lost a lawsuit because it was showing that the bias that they had, right? So doesn't necessarily need to be ethnicity, gender. It could be even mispresentation or basically kind of like a proportionate result. The other thing is that you need to always account for rare classes, which you all have heard it by now, this one. So if you have a model that 99% of time is negative and 1% of time is positive, even just printing 0 means 99% accuracy, correct? So the other thing is that, like, if you look at this table that we have here, so you have a fusion, edema, mass, those are like you're getting a really good results. But the hernia, for example, it's like it's not comparable. So the 5%, 5% in medical is a lot, right? So it's like you have a 5% basic error difference. And when you look at the result, you understand that, okay, for hernia, we only had 100 data points. And compared to the other one, we had like 10,000 data points. So that's kind of like a rare event. But they also, I always say that, remember in healthcare, if you work at any time in the healthcare, having a rare event doesn't mean anomaly. You cannot just remove a disease because you only see one time it occur or 2 times it occurs. Just keep that in mind. Or you cannot also upsample disease. Okay, so keep that in mind. And this is like a common conversation. Machine learning engineer says, I did well on the test data, product owner, but this doesn't work. But I did well on test data. It's like a common trend, right? You will say, I have said that so many times. So you will also say that because it's a reality. If you only have a test data, you know that to something that you can hold on to, that's how you can basically report. Now, it's really important for you to establish a baseline. Again, baseline we have talked about this could come in a different ways. Could be you have done a study before, your company has a product, similar product before, or you just bring humans, basically ask them to annotate the data from your baseline. Here, for example, in speech recognition, you notice that the accuracy that you have is unclear speech when there's no noise in the background, 94% accuracy. Human level performance is 95% accuracy. If it's car noise, you notice that your accuracy is 89 versus 93. With people noise, 87 versus 89. Low bandwidth, like audio, 70 versus 70. So the question here is that, well, if I have this baseline like this, what should I work on? What should I improve here? Like if you look at something like this, which one would you improve? Car noise, because you have 4%. All right. So now, what if we had additional information, and let's say we also had another column that was saying that number of data points, and you notice that let's say for the first one, clear speech, you have 1 million records. Car noise, you have 10,000 records. The other one, you have 100,000, 100,000. Then what? Which one?
Clear speech.
Why clear speech?
There's a lot more data.
So you have 1 million records, 1% of 1 million records, right? That basically how many errors you will get versus the other one that so how much data you have can easily impact on what is more important. If the data is kind of like if you're like a similar bucket, similar size, then you focus on the one that has the highest human level performance gap, basically. So same thing goes for like a structured data. You basically need to be sure that you have some sort of like some way of doing comparison. In the structured data, it's easier because especially if you have a model, you already have a label, you can compare the result. In unstructured, it's more difficult, especially when you deal with image, audios, transcripts. It's not exactly apple to apple to the comparison, so you need to account for some lossy comparison, basically. Now, the why we need to have baselines. So the first thing is that baseline give you irreducible error or base error. That's an error that it always exists basically for you. We can use HLB again to as our baseline. We could use older system. We could use literature search as our baseline. All of this basically helps to have something to compare, because when you build model, the whole idea is that I'm building something. How should I know if it's good or bad? But you need to have something to do constant comparison with. And that again could come on your CI. Well, you need a baseline when you do tests, right? Some comparison to something to compare with, even if it's you are doing a like prompting, right? So you need to ensure that every change that you do, whatever result you get is always remain the same. You know, it's kind of like if you, I don't know, a word in your prompt changed, you are not going to get a drastically different result. So, tips for a start basically is that when you try to do a model analysis, model performance analysis, or error analysis, basically what we call it, try to just change a little, do a training, do error analysis, and continue. Don't try at once to change so many variables in your model, because that way you don't know what is causing the improvement or what's caused the basically drop in your performance. But it's a cycle, basically. You are going to continue on that. Now, and we also have talked about this before, but the last line is more important. The reasonable algorithm with good data often outperforms a great algorithm with no good data. Just that same concept of garbage in, garbage out. Doesn't matter how good is how large is the model. Your data is bad, the result that you are going to get is also going to be bad. Now, so should you take into account deployment constraints when picking a model, right? So there are two answers here. Which one goes for you?
Yes.
You have a baseline already. So that's right. If you have a baseline already, then you need to account for it. If you don't have a baseline and your goal is to basically to just determine what is possible, if it's working or not, then you don't need to account for it. So you need to figure out where you are standing. You always need to do some sort of like a sanity check. Basically, sanity check means that if you want to build a model, you want to be sure that does this model work for my application? The easiest scenario is that overfit that model to the data, to a training data. If your model can overfit, what's overfit means? Anytime after the training is done, if you pass any training example, it should accurately say the answer. If the model can do that, what does it mean? It could learn, it could memorize it. If a model cannot even memorize the training data, then it cannot learn it, right? So that's a quick sanity check. Just pick a subset of training data, overfit it. If it worked, you can continue with that model family. Otherwise, change the model family. All right. So the next thing, let's talk about error analysis. So let's say you're building a model, and you basically notice that, okay, I have some label, I have some prediction, and depending on what's the noise in the background, you're basically doing a comparison. All right. So you will notice that, okay, there are some differences between what was told in the audio and what's basically your model predicted. So if it's basically a visual inspection similar to that, like a phone scratch that we saw before, or if it's like a product recommendation, doesn't matter. Your goal is that iteratively to go over this data and change tags. If you see as part of your error analysis, the model makes a prediction and you're like, doesn't make sense. Why this is an error? This is something that I personally did as part of one project, and this was like an NLP. We basically got some false positive, and we were like, we don't get it why this generates false positive. The model is pretty good. What we did, we picked the data that was false positive, and we searched through our training data for similarity, found any document, any training data that we had, which contextually was similar to this one that we had false positive. Then we went over the label that those ones they have, and we found mixed result. So we had bunch of same file was class positive, bunch of same file was class negative. So that basically, just by looking at the prediction of doing error analysis, we basically went back, look at the training data, we found the error, we fixed the tags basically, or the labels, and continued. Right? So that the error analysis doesn't mean just your model. It could mean that you go back to your data, try to do root cause analysis to understand why something like that happened. For example, another thing is that of all the data with that certain tag or label, what fraction is misclassified? What fraction of all the data has that tag? To sort of give you some idea, like that means, let's say you have an image of a cat, 20% of your data is cat, and from that 20%, you have 5% which is misclassified. You're interested to see like what's going on. If it's the number is maybe small, like it's like a 0.5% misclassified, maybe you're like, okay, not going to invest in it. But if it's like a 20% data, 5%, 10% error, then you need to probably spend some time on that. So the next thing is that prioritizing what to work on. And that comes back to the question that I asked earlier. So let's say you have gap to human level performance, it's like 1%, 4%, 2%, 0. And when you look at your data, the first part, clean speech, is 60% of your total data set. Then the next one is 4%, then it's 30%, then it's 6%. So when you do multiplication, what you will basically find is that if I work on clean speech, I get 6%, basically 0.6% improvement. If I work on car noise, I get basically 0.16%, improvement, and the next one is 0.6, and the last one basically no improvement, right? So it gives you some sense of how much improvement you get if you prioritize to working on one versus the other one. Now, that's the same thing. The next thing is that a skewed data set, which I know most of you these days you're doing an NLP because of the AI, but at some point you will iterate back on building machine. After the bubble basically burst, you will start building machine again. And then that's where you start dealing with the imbalanced data set, which was the main problem exists. Also remember this, there's a hype right now, everyone builds AI, LLM. But at some point, someone needs to build the classification models, right? Why? Because AI cannot get the time series data and make a prediction for you. You need to see the entire history to learn it, right? So someone is still building those models, right? You might not be you at the moment, but you at some point in your career you will work with that. So when you deal with the examples or data that you have, skewed data set or class imbalance, I'm not going to spend much time on this, I'm sure you know, but you need to figure out certain metrics that you want to work with. The confusion matrix, basically. Find out precision, recalls, I don't know, F1 score, whatever you feel like it accounts for that imbalance. You need to basically use those types of metrics. Don't go with accuracy because, again, accuracy is not good for imbalanced data set. Now, the next thing is performance auditing. So performance auditing, there are certain auditing frameworks that you need to keep in mind, for accuracy, fairness, biases. Basically, you need to do some first, sit with your team. You need to brainstorm these ideas, like, okay, what we are going to evaluate, how we're going to evaluate that. Figure out basically what's the prevalence of the specific errors, performance of your rare classes versus the other classes, performance of subset of your data or data slicing, basically. You need to brainstorm those and decide of how you want to evaluate, how you want to move forward with that. Figure out some metrics that you want to use for this evaluation, F1 score, or I don't know, like false positive, false negative, whatever is more important. Be sure that you discuss with whoever is the product owner in the team or the company that you are, because again, from your view, engineering view, you might say that, okay, we have 99% perfect, basically recall, means 99% of the important cases you are finding, but we have a precision, let's say, of 96%. And from your perspective, it's like, okay, that's great. But if you talk with the product owner, because they sit with the customer, they come back and tell you that 4% could cause something called user fatigue, because it's kind of like you're always creating false positives. You know, doesn't matter if you do great on building the detecting the like whatever you're like doing this like a disease, but every time imagine every 104 patients basically you misclassify them. So over time you basically build up like some sort of like a wrong reputation. So you need to account for those types of things also. And the best people to talk with is the product managers, business owners for those. Now, I'm not going to go over this one. So these are all like example of data-centric AI, which basically you focus on improving your data, just iterate over your data. But we also talked about model-centric, which is the idea of like making your model better and better. Now, we have talked about hyperparameter tuning before, which is just simply using some packages to do the search for you. But there is a new study, there's a new field in basically called NAS, you know, or AutoML. So AutoML is the idea of can we build machine learning models automatically? So one of the subdomains of AutoML is NAS, Neural Architecture Research, which the idea is that could we, in an automate way, build neural networks instead of we going one layer at a time, adding layers to each other? Could we have a process that could build neural networks, especially when it comes to larger networks? Who's going to build those? Are they doing those manually, or is the process of adding and evaluating? So that's basically the idea for NAS. We need to also keep in mind that you have two sets of parameters, trainable parameters or hyperparameters, trainable parameters, anything for your neural network. Or the model weights are the trainable, hyperparameters are something that you set ahead of time. Now, let's go here. It's a cross tuner. I'm not going to go on this. Now, when we talk about the AutoML, basically the idea is that we want a brain, or basically we want an algorithm that you start with the data and there's some model development, deployment, whatever, but we're focusing on the model training. You want that model training part to be automated, but you are still going to control it, but you're going to control it by defining what goes in it. But you want the algorithm to build it upon what you basically define. So when we talk about NAS or neural architecture search, there are three main components or basically definitions to keep in mind: search space, search strategy, performance estimation strategy. So those are the three main components to have a NAS. What's the search space? So search space, the idea is that you want to build a neural network. Let's say I want to build an image processing. I know by default what layers goes into image processing. I'm going to use some sort of like a convolution, dropout, batch normalization, feed forward, and so on. I'm not going to add LSTM in it, right? So because I know what layer goes in it, my search space will be a bucket containing either the layer names or a smaller neural networks we're going to talk about. The search strategy is the idea of like, okay, how to search through the space that we have and pick the correct next layer or correct next architect to move forward. And using from this search strategy, you will build the next neural network. Then you need an evaluation, basically, a strategy, which is a technique to pick the new model that you built, evaluate it, and gives a feedback and to the search strategy. So search strategy uses that feedback for the next iteration to pick the next layer. Yes.
When you say about layer things, like putting research space, do you also mean like having the number of hidden layers as well as the number of neurons per layer? Like those also be specified or not?
That's a great point. We will see it. So you could have a version that you predefine those,
yeah,
or you could have a version that you actually let the model decide.
Oh,
right, we're going to see it. It's coming up. So these are the main three components that you need: search space, search strategy, performance evaluation strategy. Now, this is again NAS, part of some field called AutoML. Let's understand the search space now. So there are two types of search space: macro and micro. Macro is
In the search space, does it try all possible permutations and to decide?
We're getting there.
Okay.
We're just right there. So we have two search spaces. You have macro and you have micro. Macro, the scenarios that you can think of macro like in when you build a neural network. I don't know equivalent in PyTorch, but in TensorFlow Keras, you have two types. You have a sequential, you have a functional when you build a neural. In sequential, you basically put one layer, next one comes after, next one comes after. So in the functional neural network, you build these layers separately and then you connect them together differently. Like they don't need to be sequential. Macro is kind of like a sequential. You define input, layer one, layer two, through output. That's a macro search space. So you define layers. Micro, on the other hand, you don't define layers. You define pre-defined block of layers. So in micro, this is one input on the right. You're going to provide multiple of this. I'm going to talk about why. But macro is layer per layer. Micro is block per block, basically. Now, when it comes to macro, you could have chain structure, you could have complex search, basically that's basic, it's kind of a complexer search. It's kind of like a functional, basically. But when you do the search in micro, this is what basically it means. So let's say, actually, let's go one back before we ask macro. Go back to what you asked. So let's say you are trying to build, again, certain types of convolutional model. You want to build a deep convolutional model that basically gets a large image, like these images that you have a really high, basically really high bit map, or basically the high resolution, and you want to do convolution and extract certain feature at the end and make some classification. And your goal is to maybe add, I don't know, like 100 layers. All right. But you don't want to do it manually. So as part of your macro search space, you provide the model with predefined layers. Okay, we're going to talk about the hyperparameters of the layers, but just for now, let's assume layers are fixed. And you basically let the model one layer at a time to decide add. So let's say at first, like a second layer, the model adds a convolution, and it wants to goes to the third one. It wants to see, should I add another convolution or should I add a pooling? So one time it adds a convolution and it does a comparison. How good was the result? Then it removes that and adds a pooling and says, okay, how much was the impact? Is it better or worse? So it basically iterates through these combinations to figure out which one is better. For now, assume that the hyperparameters are fixed. Okay, we're going to talk about the hyperparameters. But when it goes to micro, the idea of micro is that, let's say you have this knowledge that, especially, let's connect it to a transformer architecture. You have the knowledge that attention, right, comes from let's say the self-attention. You need a query, you need a key, you need a value, right? You know that as a block, you can build an attention layer. So instead of letting the model just get the query separate, key separate, value separate, and let the model figure out how to use it, you predefine an attention layer, which is more complex. It's not just one layer. Technically, a series of things happens in it. And you tell to the model, this is an option that you can pick wherever you find necessary. Then you provide another set of layers, like another smaller neural network technique. So you, instead of providing layers to the model or to the algorithm, you provide a smaller neural networks that you know they will work in this scenario. You have been proven by other in the studies or in the work and stuff like that. And you basically tell to the model that pick whichever you find important and add it to the next one. Like stack them on top of each other in the order that you think is more important, or doesn't, and you don't need to only repeat once. A layer could be repeated multiple times also. So in the micro search space, this is basically what's going to happen. You stack these predefined blocks of like layers or smaller neural networks on top of each other and basically continue. Okay. Yes.
Can you just remove these predefined blocks if it feels like it's not giving the optimal performance and it has some better alternative?
I don't think so. So on one of the, so we are calling this AutoML, but there is still one piece that's not automate, and it's the search space. It's still a human need to define what you can choose, what you can select. It's not fully automated, right? So maybe it's a newer field, but maybe in the future it becomes to the point that you can basically manipulate or basically remove something from certain block. But at the moment, these are like a fixed definitions, right? Yes.
So for micro, you're saying that you kind of inject like more control, more specifications. For micro, it's more like loose guidelines. Is that right?
So in micro, you have a more control, right? Because you predefine architects. You're saying that I know how this works. In macro, you give layers and you tell the model, I know these layers work, but you put the way that you. So it's kind of like the model in micro has less control in compared to macro. Macro basically is just we can select and add and drop. Yes.
In this case, like the model can be biased towards one strategy, like we can, how do we integrate that?
We haven't talked about learning yet. We'll get to the learning and hopefully that will answer your question. So search strategy. Now that comes back to basically what you're asking. So when we talk about search, that means you have this search space, which is layers or models, like a bucket. How could you search through that? And because what you want to keep in mind is that let's say you have three types of layers, right? You have CNN, you have dropout, and you have pooling. Okay. And you have three layers, but every layer has different parameters, right? There's different hyperparameters. So because of that, you basically end up with this search space that you could select from. Or the algorithm can select from. So how would you search through this space, pick the correct layers, pick the correct basically hyperparameters to ensure the final result is correct? So there are some search strategies we're going to talk about. The first one is grid search, then is random search, Bayes optimization, evaluationary, and reinforcement learning. So grid search, which kind of makes sense. It's kind of like a brute force, right? You basically go through everything, right? And it makes sense. It's kind of like it's more expensive. It takes a long time. So if your search space is large, doing a grid search is going to take forever. If your search space is small, then yeah, maybe it makes sense. Random search is also kind of similar to that, but you're just doing it randomly. It's instead of just brute forcing, you're just doing a random search. Then it comes to so it's like a grid search and basically random search. It's kind of like you just go through all of it. Then it comes to Bayesian optimization. The idea of Bayesian optimization is that we basically say that the model performance, how good is your model, that accuracy score, the performance, comes from a distribution. If you build 100 of the same model, and every time you get a final performance, you end up with a distribution, right? So the model performance has a distribution, basically. And given that, we normally assume some sort of like a Gaussian distribution by law of the basically central limit theorem, or law of large numbers also. We basically say that we know the performance of the model comes from some distribution. And we are going to use that knowledge to decide if I should go with this input, which means certain CNN with some parameters and then certain this with some parameters and so on, or I should go with this. So you basically you have a model and you want to say that should I add this layer, and that layer is, let's say, it's a CNN with some parameters. You just use that. You go against this definition of distribution that you have, and it's basically it's kind of like, so because it's a curve, right? If you fall on the here, basically, you know, let's assume that you basically get you end up with a lower number, right? So you want something maybe here, right? So it's more common for you to fall in this region, but you want to do the one that's give you a higher basically score. So you use that knowledge in order to estimate, is this a good basically parameters or good layer to add or not? And you look through. So base optimization is pretty fast. Like if you work with scikit-learn, you work with Keras tuner or hyperop, all of this, you will see that by default, they do the base optimization. It's pretty fast for doing these types of search.
A question.
Yes.
So what's the distribution performance with respect to? Like, is it other different models or just?
So you start, let's say at first you start that and you don't have a distribution, right? You can over time build this distribution, right? So you first add a layer, and that layer, let's say, gives you one number. And then you compare the other layers. Like let's say you have 5 layers. So for the first layer, you're going to check all 5 individually. And then let's say you get something like this. That's the performance of the model. Let's say this is the F1 score. Maybe let's do something like this. Get something like this. And then you pick the one that's highest. And then you go to the next layer. And then you add. Over time, you basically end up with this. And by basically the central limit theorem, it automatically becomes a Gaussian or in the center, right? And that helps you to use it basically for kind of like an estimation to detect, to do a detection. So the next technique is called evolutionary methods, which is pretty interesting idea. So the goal here was that, so you have, let's say on the left, you have 10 predefined layers or blocks that you want to select from. And your goal is that to figure out which one of these are good. So in this basically approach, you go over this, that again, the number 10 is just random for the example. You go over the 10 and you figure out among those 10, the 2 in the yellowish color, they are the top basically performance, top layers or top smaller neural networks. They have the best performance. We call those parents. Then what you do, and again, why 3 blue, that's also your choice. You pick those 2 and you what we call it offspring. You combine them in a certain ways to build child from those 2 top performing layer or top performing neural networks that you have. It could be any manipulation that you do to those ones, because you're like, okay, I know this architect works really good, so I'm just going to do a little manipulation and I'm going to build this 3 offspring. Then you go from pick those 3 offspring and you remove the 3 of the worst earlier basically versions that you have. So you replace those. And then you go back and you repeat this process. The idea will be that you keep doing this by over time, you end up with these blocks of neural network that they have the highest improvement gain over time. Like every time you add one of them, it gives you the highest improvement because you basically manipulate them. Whose question was about manipulation? Editing, it was yours, right? So that becomes one idea. So the model decides and goes over and basically remove, edit, build its own network, but not exactly just kind of like it, but it's a version of it. So you get rid of the previous one. It doesn't manipulate the previous one. You get rid of something and basically adds. So this is called evolutionary methods. And the next one is a reinforcement learning idea, which the idea here is that we want, and agent to figure out, given a search space, figure out what's the best layers that we should add. So, you guys, how many of you guys know about reinforcement learning? Not much. Okay, so we can let's understand what's the connection here to what we did. So in reinforcement learning, let's say this is the agent is a robot, and you want to teach this robot to walk, and the idea is that in reinforcement learning, we don't have an environment, like we don't have a code, like it's not like a not that we don't have a code, like we don't have a model code. It's not like in machine learning, you have a data and you go learn a model. In reinforcement learning, all you have is a classroom, like let's say this is the environment, and you have set of policy and actions. Action means that it's this robot can walk forward, left, right, backward, 4 directions. And from that, you define one goal. And the goal maybe for your robot, because let's say you are trying to teach the robot how to walk. The goal will be every second that, or not every second, maybe every step that you take, plus every second that you're standing and you're not falling, you get a positive reward. Your goal is to maximize this reward. So you basically, until your battery dies. And the robot doesn't know anything, it just knows the actions and the environment. So it basically iterates over and over again, and it learns how to take actions, where not to go, which maybe location to avoid, and stuff like that. After you have all of that, you go over that, which is that search space is the space in the class, that the space that robots can basically search. After the robot went over all of these and found out the best actions, you basically create something called a policy. Policy is a mapping between the state and the action. If I'm here right now, at this time, what action should I take? So you're looking at the policy. Policy tells you that from what we learned, you should do this. So in the scenario that when you were trying to build a neural network, the idea will be that you have this search space and you don't know how to do that. So the agent job is to try out and figure out. And over time, basically is adding, learning, okay, this was a wrong decision, I'm going to remove it and keep doing that. Over time, it will reach to some sort of like a policy that if I'm at the layer 3 and I already have done a convolution, next one should be a max pooling. Because previously I saw that I learned this is a better performance. After a max pooling, and because the previous one also was a convolution, now I need to do another convolution, and so on and so on. So that becomes the idea of reinforcement learning here. One of the interesting papers that they combined the reinforcement learning and the recurrent neural network. So what they did, the authors, basically what they did was they built a text generation model, which its job is that given an input, it will predict as a text what should be the layers. So you provide tokens ahead of time, and let's say the model predicts LSTM as a text, parentheses open, 128, comma. So the model will predict as a text the layer specification for the next add. You pick that output of the model, add it to your, basically you have this control agent, this converts the text into the actual layer, and you add it to the model, and then you evaluate it. When you evaluate it, in order to understand if it was good or bad, like you have this agent, like a reinforcement learning stuff. Let's say it tells you it's good, and you get 5 points, or it tells you it's bad. What it does it does back propagation, gradient descent, updates the text generation model that you have, because that's job is to build textual representation of the layers based on what it has seen. So the author did a really interesting work. So you can basically have this RNN, LSTM generates layers for you, and you basically add and iterate. So instead of you trying to actually learn this search space, which is really expensive, or even this one, which is expensive, you just update a neural network, which is a simple, like a gradient descent strategy to build layer representation for you. Okay. All right, so now all of this basically requires also for you to have a way to measure the efficiency, because these types of model, they run in iteration, right? So you just at every epoch or every episode, what it does, it adds a new architect to the layer to your model and evaluate it and decide. But the question is that how should you do the evaluation? Because if you using a validation accuracy to decide if it's good or bad, think about the cost of that. Every iteration, every epoch, when you add a layer, you want to test your model against a large amount of validation data that you have to see if it's good or bad. That's going to be super slow, super expensive. So validation is not going to be it's not going to be an doable, computationally efficient, basically a strategy. There are some alternative here. One is the lower fidelity estimate. The other one is a learning curve extrapolation and weight inference with network morphism. Lower fidelity estimate. The idea is pretty straightforward. Basically, it says that instead of using the entire data, use a subset of your data. Instead of using a full image, maybe convert the image to a lower resolution and then run the test against those ones. And if you do filters, don't do so many filters for evaluation, just do a limited number of filters, you know. The other one is the learning curve extrapolation. And this happens in most of those libraries that you see, they do learning curve extrapolation. The idea is that you guys have done some hyperparameter tuning, right? Which library did you use? Random social. So you notice that when you define it, there is a parameter that you need to define which says how many epoch, after how many epoch to stop, right? So let's say you have defined this to be 8. That means maximum 8 epoch, you continue with one definition, one layer definition or model definition. The way that this this strategy works is that, let's say your model goes here, and your model after 3 epochs, because it already noticed the way that this the curve is moving, it's like, okay, I can extrapolate this. After 8 epoch, I'm going to be here. Kind of estimating, you know. So this technique, instead of the model always goes to the end, it basically predicts. The only time it goes to the end, if there's a fluctuation, it's hard for the model basically to predict. But that would be the idea. So that's why this types of algorithms are doing fast prediction, because they kind of extrapolate where it's going to be in I don't know, 10 epochs or 8 epochs.
Is this similar to learning rate scheduler that we put in, like after a certain epochs, it should reduce or enhance the learning rate?
So do you mean warm start?
Yeah.
So no. So in the idea of that learning rate scheduler is that if you doing a gradient descent, right? We know at the beginning of every training, learning is kind of like a fast. What does that mean? That means when you start the model, the first time sees the data, there are lots of easy things to learn. So in the idea of this warm start with this learning rate, basically what you do, you quickly increase your learning rate. You want basically your learning rate to be super high. It goes to super high because it learns at the beginning. I don't need to take a small step. I can jump, I can run. But then after a certain number of epochs, you want that learning rate to decay quickly. Right? Because you want it to now to be sure that the steps that you take is kind of like a fine grain. So that's the idea over there. So you still do the full process. Here you extrapolate. That means I take 3 steps, then I'm like, I have a gut that I'm going to be there after 8 steps. So I'm not going to continue, I'm just going to mark. It's kind of like a gut feeling over where you're going to be. So So the next thing is that weight inheritance or network morphism. The idea of morphism in networks is that if if you change a function, as long as the functionality, the inherent functionality, that doesn't change, that's kind of like a morphism. So the idea here is that could we transfer a knowledge from a larger model to a smaller model without losing the information, and that way it can run on a smaller amount of GPUs. So that's the idea of the network morphism. No, we don't have. But this comes, I think it comes back to the next slide. But this comes back to the same distillation that we talked about before. Okay. All right. Before I go to the next slide, end of every slides, the labs that I'm not going over, those labs you have already. Most of them also have a video recording on the repo, right? So I highly recommend you to just go through this one. We will have the Docker lab, and then we will move to the next labs are just all deployment. So the only thing we will do is the Docker or containerization, basically. All right, so so now we're going to talk about distributed training, high performance modern distributed training. Especially these days, you all basically need to do something like that. Over time, companies will start to, at least that's my guess, companies will start building their own LLMs or like a large language models instead of just trying to buy it. So you all somehow will do something like that. So up to this point, training the models was easy. You basically could have like a one GPU, you build a neural network on it, making a classification on it, image processing, and so on. So this type of thing was easy. Even if you had two GPUs, it was kind of like a easy process. But things has changed now, and the problem is that you have more data, you have larger models, you have longer trainings, and you need to ensure that you have a strategy that could let this training pipeline run without breaking down. Why? What happens if it breaks down? What do you think will happen? Let's say you're using like a 10 GPUs, and like what happens if it breaks down?
All the efforts go in the wind.
What was that?
All the efforts go in the wind, like whatever's paying.
What? GPUs are expensive. Most of the companies, they don't have GPU. You rent GPUs. When you train these large language models, it takes days. And normally you have hundreds of GPUs basically running. So that's a lots of money. Now imagine you made a mistake, and after 3 days, this pipeline broke down. Right? So you can see that how devastating it is there. So you need to be sure that you account for those types of things. So that's why we brought out the distributed training approach. So there are two main strategies: data parallelism, model parallelism. Okay. So data parallelism is any time you have a model that can fit into your VRAM. VRAM is the virtual RAM on your GPU, basically. Anytime you have a model that you could load it directly in your GPU, right? Then you can use this DD or data parallelism. The idea is that you, let's say I have 3 GPUs and I want to train a model or fine tune a model or something like that. And every GPU that I have could get an exact copy of the model, because the model is not that large, or my GPU is too large. It's good. So every GPU gets a copy of your model. In that scenario, Now you can train this model over 3 GPUs by distributing the data across these 3 GPUs. So you basically what you do, you break the data down into like you shard your data and you distribute it among different GPUs. It's important to remember all these 3 GPUs will have the same model. So if that's the case, you need to somehow combine them. Otherwise, you end up with 3 different versions of the model, right? So that's the data parallelism. We're going to go in details on this one. The next one is model parallelism. And that's where you have this model that you cannot even load it into your GPU. You cannot even load it on your computer if you have 1 GPU. So many of the large models. So in those scenarios, you need multi-GPUs. So if you have multi-GPUs, that doesn't mean that every GPU again gets a copy of the model. No, you're going to break down your model into shards. So instead of sharding the data, you shard the model. Your model basically will be split into chunks. Every GPU will get a chunk of the model. So it kind of becomes like a sequential GPUs that they are feeding to each other. Okay. And then in this scenario, you can do data parallelism also, but we'll see that. Now, so data parallelism, model parallelism, then the next thing comes called pipeline parallelism. And the idea of pipeline parallelism is that you shard the model, you also shard the data, like the entire pipeline together, by ensuring that we will see details on this one. But by this way, we ensure that the model will it fits on the smaller GPUs. At the same time, we are passing smaller data to the models to speed up the process. So that way, the next GPU is not waiting so long for the previous one to finish the work. It's kind of like a speeding up the process. Yes.
So how does the model sharding works? Are we sharding it by layer and then parallelly training the layers, or how does it work?
Yeah, you need to do layer. So it's a sequential sharding. So think about let's say you have 5 attention layers, right? And the way that works is that every attention layer technically feeds to the next one, correct? So you put the first attention layer into a GPU 1, second attention layer into a GPU 2, third attention layer in GPU 3, and so on and so on. And that way, when the data goes through the first one feeds to the second one, and so on.
But then how is it training parallelly? Because when I think of parallel training, is basically all of them start at once and
No. So here the idea of parallelism is not that they all need to run at the same time. If without doing that, you cannot even load the model, right? So you shard the model. That way, basically, they can run. You can train it, but it has other issues. We're going to talk about it. It has that's called the bottleneck here is in communication, right? We're going to see that soon. Then the next one is tensor parallelism. And just basically the idea will be that to pick a tensor and then try to split it, for example. The tensor parallelism happens a lot these days, especially if you work with PyTorch. If you try to do, I don't know, some sort of like a matrix multiplication. So if you have, let's say you have this one, 1, 2, 3, 1, 2, 3, and you try to multiply this by something like this. And then you want to multiply this by something like that. In tensor parallelism, what you will do is that you split this process into 2 operations. In one operation, you multiply this by only the upper part. So one GPU does that. 1, 2, 2, The other way.
Between.
2 by 3. This will be transpose, basically.
Yeah.
Transpose of this. Then imagine this is the other way around. So one GPU does that. This one times this transpose of that, then times this. Okay. The second GPU does this times that and times that. And you concat the result together. So you can get the same result by basically split these tensor operations. So now imagine you're working with like a large transformers or basically dot products anywhere that you have this fully connected connection multiplications. And you can basically have multiple GPUs, so you can split the process by splitting on tensor axis, basically. Yes.
Is this related to Google's TPUs?
Not directly. So yes and no. So Google TPU, NVIDIA GPUs, or any GPUs basically that they allow you. So GPUs basically are for matrix multiplications, right? So anytime you deal with GPU, TPU, NPU, those are basically allowing you to do a faster multiplication, do more parallelism, because you have more cores. So then you can utilize something like that, right? So if when you work with Google TPUs or NVIDIA GPUs, you definitely can utilize this, right? When it comes to matrix multiplication, this is a faster process.
Is there any downside to Google's TPUs?
Not a good person. So the downside, I think the main downside is that you don't see it. Right? You cannot buy one.
Oh.
Right? It's for Google. Right? It's great. You know, it's proven. If you think about it, it's the only company that they build their own infrastructure. They have their own basically accelerator, and they do their own AI on it. Every other company buys it. This one shares it with the other one, and so on. So from that perspective, they know something works really good. They don't share it with anyone. So, but yeah, I can't speak to that because I have worked with it, but most of the time we work with GPUs because TPUs are not that available.
Like fundamentally, what's like the biggest difference on the board?
I'm not gonna comment on that because I really don't know fundamentally how. Like I know what kind of operation kind of goes through it, but I never was that big fan to look into TPUs to see how much the improvement they get. It's like a but if you found, please let me know. Yeah, yeah, I can answer on that one. If it was something that available for everyone to work with, maybe you would have get more interested to learn about it. But it's only available if you work on GCP, rent a TPU. But otherwise, it's not available, right? And the other one is the hybrid parallelism, which is you basically combine all of these methods together. Now, when we talk about data parallelism, this is basically what you will see. So you have GPU 1, which is working node 1, GPU 2, same model loaded into each, and then you get a different subset of your data. As part of the training is that you have split that runs on these 2 GPUs. But one thing that's really important here is that, okay, if we have these 2 subset of the same model, and we are training it, after one epoch, now you have model 1, you have model 2, right? So what will happen? What do you think you should do? You end up with 2 different models, right? Because they, after back propagation, the weights are kind of become different. What would you do?
We will evaluate which one is more relevant to us than we discard the other one.
Where's the team that they are doing the learning? Okay. Tell me, what would you do? You have 2 models, right?
Can we concatenate the weights of it?
Concatenate the weights.
Average.
Average. Who said average?
Arbitrary.
Yeah. So you do some sort of like some operation that's kind of like a all reduce operation, right? Yeah, so you basically get, so the way that it works is that model one has some gradients, provides you the gradients or weights. Model two does the same thing. You get those and you kind of like average those, and using that average, you update the original model. Right? So that way, the knowledge that you're receiving from two separate models is kind of like combined into the global model. That's a similar idea in federated learning. You have these different nodes or workers that over time they will diverge from the original global model. So you need to ensure that you kind of align them together. Yes.
This idea is same as gradient accumulation, right?
That is correct. So let's come over here. So now there are two ways you can do this. We're going to talk about that. So synchronous training, asynchronous training. Synchronous training is the scenario where we say that you're using something like an all reduce architect. That means every model basically works in sync. They need to work at the same time. Start, finish, when every model finished to training and then or that epoch, and you get the information all reduced. So that's a gradient accumulation. The asynchronous training, on the other end, the scenario is a bit different. It's where you have basically you have this server, which is called parameter server. So let's say you want to do asynchronous training, and you have 4 GPUs. In this scenario, one GPU doesn't train model. One GPU is responsible for connecting to other GPUs, get the data, update the weights, update the model, and continues. So that GPU is called parameter server. So 3 of your 4 GPUs get the model, a copy of the model, and they do the training. But in that scenario, they don't need to be synchronous. They don't need to work together. So GPU 1 keeps going, and every time just sends the updates to GPU 4, which is the parameter server. GPU 2 does the same thing. GPU 3 does the same. And they don't need to wait. GPU 4, its job is to align these updates that it receives over time and basically combine them together and update the original, the global model. So at the end of the process, GPU 4 will have the global model updated using the information it has received from every other models, every other GPUs. Does that make sense? All right, so now the one idea is for training this model is that could we make the model to be aware of this basically distribution? Because if the model is just trained by itself in isolation, it doesn't know that it doesn't know about any other part of the like any other GPU that does the same thing. Think about when we did quantization, we also had quantization aware training. So here is kind of like a similar story. Could we do distribution aware basically training? And then you got both libraries, they have two easy solution for it. In TensorFlow, you have tf.distributed.strategy. And in PyTorch, you have torch.distributed. So both of these are like just one line code that you add to the beginning of your neural network, which allows the neural network to run in distribution. Okay. So the way that works on TensorFlow, you just need to wrap your neural network, the part that the code runs, in one of these strategies. These are the available ones. One device strategy, mirror strategy, parameter server, multi-worker mirror strategy, central storage, TPU strategy. They have for themselves. If you go to PyTorch on the other end, you have the following: single process, multiple device, fully sharded data parallelism, distributed data parallelism, tensor parallelism, pipeline parallelism. And if you are a AI follower, you will be you know that most of the models and papers that comes out, they're doing FSDP or some sort of like pipeline parallelism instance. So on the one device strategy, what's that? That's a scenario when you trying to prototype something and you have just one GPU, so you basically run the code on one GPU. That's one device strategy. It's just for prototyping and quick research. Mirrored strategy is same as data parallelism, when you can mirror the model into multiple GPUs. So if you have 2 GPUs, 3 GPUs, and you just want them to do data parallelism, you just need to wrap it in mirror strategy. If you are using TensorFlow, in PyTorch, it's TDP. Then you have parameter server strategy, which we just talked about. The idea was that if you have multiple GPUs and one of those GPUs will be responsible for combining the information from the other GPUs. That becomes the parameter server strategy. Then you need to account for fault tolerance, and fault tolerance, it's what we talked about. What if something broke? Then do we lose everything? So you need to be sure your data, your pipeline basically has some sort of like a backup and restore basically functionality. Backup and restore means that if by any chance one of the nodes died, one of the GPUs died, and everything will stop, let's say, when it restarts, like your Kubernetes, like your GPU service comes up again, it's not going to start from scratch. It goes to there's a location that it writes there, and it reads the latest basically parameters and distribute those parameters to every GPU, and it continues from there. So this idea of fault tolerance is that it accounts for the current updates and the current state that you're in, even the data, like what index we are at, and so you can basically write those to your machine. All right, I'm going to pause here, give you a break. All right, let's continue. Okay, so the next types of strategy is single process multi-device SPMD, and this is PyTorch related. So the idea basically here is that you are doing one process, one operation, basically one model, and you break it down into multiple based on multiple devices. It doesn't have technical distribution, it's just breaking down of the task. Then fully sharded data parallel FSTP, which is the most famous one on PyTorch library. The idea here is that it's a technically a data parallelism concept, but what it does, it's allows to basically for you to shard the parameters also. Parameters gradient optimizer across multiple GPUs instead of basically replicating them. It reduces per GPU memory usage. So kind of think of it like this algorithm, this strategy, what it does, it instead of every GPU to calculate every gradient, they do soft gradients. So one GPU does this, one GPU does the other one. So that way you reduce the total overhead and cost that you will have across all GPUs. Then we have DDP, distributed data parallelism, which it's kind of like a just asynchronous data parallelism across multiple GPUs. So these are technically the same as they are the same in TensorFlow. PyTorch is just the library name is going to be different. And the tensor parallelism, which is what we talked about here, that's also on PyTorch. The next one is pipeline parallelism. We will see this more in details later, but this idea of pipeline parallelism allows you to do model split, data sharding, and gradient accumulation, or all of this basically in one pipeline. So instead of doing per GPUs, you do it across one entire pipeline.
So is this anyway related to the session thread coolers or something that we use? Then it's in parallel.
If you define your session in a way that you shard the model parameters and you create the mini batches on data, technically you're replicating the same thing, right? Right. So one of the famous one here is a library called gpipe by Google. It's for the pipeline parallelism, but I think deep speed also has that, is pretty good. All right, hyperparallelism, I'm not going to go on it, it's just a combination of all of this. Now, all of this, let's assume that you have these GPUs and you know how to going to distribute those, okay? But if with the best distribution, you don't have a good ingestion, you are not doing anything. What does ingestion means? If you have GPUs where they all perfectly match with each other, but the data comes so slow, you are going to lose money. So parallelism will be useful if you also have a high performance ingestion. There are a couple of components that you need to keep in mind. First is that data at the time can't fit into a memory. CPUs are normally underutilized in data pre-processing. GPUs are underutilized in matrix operations. So it's always are issues. And you all have heard of ETL probably, right? And like in data pipelines, extract, transform, basically load, right? So the idea of ETL is that you need to be sure that you account for three things in order to have a high ingestion pipeline. So when we talk about extract, what does extract mean? Extract means to read data from either storage or from your hard drive. That's the extract. So you either read from internet, like a storage, like a cloud service, or something like a bucket that you have, or you have it on your hard drive and you need to read that. So that's the operation called extract, right? Which part of your computer will be used for extract? When you load something, where does it go? RAM. So extract is impacting your RAM. All right, so that can tell you, depending on how much RAM you have, how much data you can basically extract. Then you have transform. What's transform? All those pre-processing that after you load the data, a batch of data, all those pre-processing that you perform on it. What do you normally use for transform?
Scaling, like normally.
No, which part of your computer? CPU. CPU is responsible for any transformation that you want to do. Then you have load. What is load? Load is the process that you had this data transformed by CPU. And now you need to load this data into your GPU, your accelerator. What do you use for that process? There is one component on your machine that is responsible for temporary storage. Cache. So why cache? Cache is the closest location to your GPU. So what you do basically, you load data, transform data from CPU, you store it into a cache, GPU will quickly read from cache. So these three components will create a ETL pipeline that looks like this. So step one, extract. Let's say this is like you're training a neural network. This is like epoch 1. And you load a batch. And you have this code that basically pre-processes the data. that transform that happens on your CPU cores. After it's done, you load it onto cache, and that load by default happens by whatever library you use, TensorFlow data, PyTorch data, they do load it into a cache. So you load it into a cache, and then your accelerator or GPU reads that data. So why this is inefficient ETL? Because every step is sequential. So you read, transform, load, train. When the train is done, you go to read again. What happens? Accelerator idle, CPU idle. Those are the two pieces when you rent, for example, on GCP for your project, you pay for those. CPUs and GPUs. Right? CPU is normally not that expensive, but you still pay for some. So think about it, if you're having a pipeline that in every epoch, majority of time, your CPU or your GPU, they don't do anything in every epoch. Maybe 80% of the time, 90% of the time, they don't do anything. Think about if you let this pipeline to run for 2 hours, right? Kind of like 100 minutes of the entire operation you paid for nothing. You're not even using it. So that's why it's really important to account for your ETL pipeline and ensure that this ETL pipeline focuses on efficiency of usage, basically utilization on your GPU and your CPU. How do we do that? There are different processes that we're going to go through. So the step one is that, well, I don't need to read one batch at a time. If my RAM can load multiple batches, let's say 2. So in step 1, I read 2 batches. Now I have 2 batches. One goes to the transform to the CPU. As soon as that is done, the second one is already loaded in my RAM. I pass it to the CPU. And then I load another one. So by doing so, you see, as you go, your CPU is gaining a lots of utilization. The problem here is that you need to account for how much data you can load. So you need to play with that batch size. If your batch is somewhat too large that you can only load one in the memory, maybe make your batches smaller so you can load multiple batches, right? That way you have a better efficiency. And then here in this scenario, as you can see, your accelerator is 100% of the time utilized. Basically your GPU is constantly working. Now, this also could be like utilized with something like pipelining. And pipelining, above we do pipelining, you prepare idle, train, prepare idle. And this is like across multiple components, cache, RAM, CPU. In pipelining scenario, your CPU is constantly working, and your GPU or your TPU basically is just whenever there is something ready, they just work. Now, how does that work? How could we do all of this? So we start with this definition. The first one is called prefetching. So when we work with TensorFlow, PyTorch, all of them, they all have this function called prefetch. So if you again, like the definitions are pretty straightforward. So if you do torch data, that's the class, and you wrap your data within that, it gives you some functionality. If you also do TensorFlow.data and you wrap your data, it gives you some functionality. One of those functionality that they give you is called prefetch. So it's like as simple as this, for example. I remember it in TensorFlow, it's like dot prefetch, and you define how many you want to prefetch. Like as simple as that. It's like just one function you add to the data. And basically as part of prefetch, what you are saying is that when you read data as part of a patch, don't just read for one batch. If you have a space in the memory, read extra. You can predefine that, like by making it fixed, how many to read. But you can also use some sort of like, they also have this prompter like called auto tune. Basically, you say that whatever you can fit in. Like you let basically the algorithm to decide how many batch it can read at the same time. So that becomes prefetching. The prefetching again is responsible for the extract. Then parallel data extraction and transformation, which is the CPU utilization, the transform. Whenever you write your code for pre-processing, as much as possible, utilize all your CPU cores. Don't just write everything sequential code. If you can parallelize, if you can use multi-processors, multi-thread, utilize those, use all of this. So as much as possible, ensure that your data transformation, which happens on your CPU, it actually utilizes all those cores, all that's possible, those available basically. So the next one is caching. Caching comes back to the load, basically. Basically, you define that, okay, whenever you load into the cache, if it's available, basically you cache more, Now, as part of the caching, there are two things here. You could cache into cache memory, but on your computer, if you just right now look at your, I don't know, most of your Apple, if it's anyone Linux, if you do HTOP, basically look at your RAMs and stuff like that, you will see that your cache is always much smaller than your RAM. It's like a 5 to 10%. You can adjust it, but it's not a good practice being. What you could do if your cache is small and you're like, I need larger cache, but I cannot account for it. The idea of this caching strategy is that you can actually, after the transform is done, whenever your CPU done with the transformation, write it to hard drive. So we write it to cache because cache was the closest to the GPU. But if it's not available, whenever in a transformation the data is transformed, keep doing that. Like you don't need to wait. Keep transform right to hard drive. Transform right to hard drive. And your GPU, basically, instead of reading from the cache memory, it will read from the hard drive. Basically, you load the data from the hard drive because it's already pre-transformed, and then we pass it to the GPU. So that's the idea of like a caching. So this is perfect. So it's just an example of I think the TensorFlow. You just simply did, that's your data set dot prefetch experimental auto tune. You basically just prefetch. Auto tune means that whatever you figure out, it's enough basically read. So on the prefetch, you will see that now it loads. Those are like a data for 3 batches, basically, the black square. So when you work on the data or parallel data extraction, which is the prefetch, you also need to account for 2 things: time to first byte, read throughput. Time to first byte basically is that how long will it take basically to read data from so if you read data from internet, from storage, not on your local machine, how long will it take for that communication? Account for that. Okay. Read throughput basically is that in this bandwidth that I have, how much actually, that's the maximum amount of data I can read, I can request, So you need to account for this if you read data from remote storage, not from your local machine. Then you can do parallel interleave. That's also like, I don't know equivalent of this on PyTorch, but in TensorFlow, you just call it interleave, which interleaves the processes. You can define the number of parallel interleave also to be auto-tuned. Like it's basically, it would decide how many processes it can go through. And then parallel data transformation, basically, the idea was that again, post data loading, input will be processed. You can write, basically, you can write this to, I don't know, like either your hard drive, or you can basically write it to your cache memory. But all of this basically could be done if you use something like TF data or PyTorch data. And it's just the equivalent of the same thing on PyTorch data. Okay. just PyTorch data has a couple of new parameters that TF data doesn't have. One is that the prefetch factor, basically just some parameter for you to control how this you wanted to prefetch. Then the pin memory basically, what it does, it allows for faster transfer between your CPU and GPU. I don't know if TensorFlow has added the equivalent or not, but they didn't have that before. Okay, that's the same thing. Now, that's also the same thing I just talked about. If we do caching, you either do it on the cache memory or you do it on a disk, and you read basically from the disk if you don't have enough cache. Okay, and this is the equivalent of the same thing on PyTorch. So PyTorch doesn't directly have cache API, but it allows you to do in memory and disk and using basically Hugging Face to read those data. It doesn't have directly the cache which TensorFlow has. All right. So those are all comes around the data ingestion. I have every semester say to students, if you're whenever you build your pipeline, your end pipeline, you need to also, as part of the submission, have a way to show how this data transformation, how long does it take for every chunk of your process on your pipeline? How efficient is this? You already get a view of this if you use what's called ELK. Okay. No, Airflow. Sorry, Airflow by default, if you with those of you that use Airflow, has something as a chart called Gantt chart. The Gantt chart shows you basically similar thing. Tells you that per process, how long does it take for this process, and what you want to look yourself also. This is a real product we built. Is if you're looking at that Gantt chart, in case you did that, if you have one function that takes a long time. It's like a long block compared to the other one, break it down. That way you might have been able to optimize it or parallelize it. If you have one function that goes forever. And that goes the same thing for your loading into your data. When you have a data, like a query comes, and you do some process on this, and you're passing it to your model, if it's not just an API call. Take a look at those processes, the steps that data goes through until it reaches to the model, and figure out which parts could be the bottom. Try to basically optimize in case it's applicable to your project. Okay. So now the next thing we're going to talk about is like this idea of the raising of the models becoming larger and larger. The problem is that if you think about it from 2014 to 2017 to current dates, models are basically increased, the capacity, the size of model increasing by like exponentially. But the GPUs or the accelerator capacity, they're only increasing by like I don't know, factors of like I don't know, probably at this point 10, right? So the speed that the accelerators are improving is far beyond or behind, sorry, the speed that the models are getting larger and larger, right? Like, so there's a problem over there. Because of something like this, you basically, that's just an idea of like the model parameters from 2014 to now. You can see the difference, like because of something like this, factor of 3. Yeah, not 10, 3. Because of some issues like this, then you need to come up with a way to build. You need to still build larger models, but you also need to find out a way to make it more efficient. So that basically brings us to 2 issues. First one is that memory concern. So when you build these types of models, well, the thing is that during the iteration, your GPUs has this VRAMs. That VRAM is limited. Why? What do you use it for? You use it for loading the model itself, model and its parameters, right? Yeah, and if any operation that happens, it basically happens on also VRAM, all those attention, calculation and stuff like that. So when you want to do gradients also, you need to store that gradient somewhere. So the first problem is that gradient or the strategies of doing a gradient accumulation. The idea is that split your batches into mini batches. Instead of having a batch of, let's say 60, for example, maybe create 8 batch of 8, and then try to do mini batches and accumulate the gradients from all those together and as one batch, one total batch. So you do from forward and backward batch on those mini batches. Then you can do memory swap. Wherever is, and this another definition for this is called offloading, CPU offloading. Wherever is applicable, you can offload certain values onto your CPU. Just instead of to be on your GPUs, for example. One other thing that was like this happens a lot is like on activations. When you do forward, you have this activation, you might need them for the backward, but the process is that you don't store them actually. During the backward, you recalculate the activations because that way you don't need to store, don't need a memory for storage. You just, as you go forward, you calculate and you forget those activations. When you come backward to back propagation, you basically recalculate those values. The other one is the activation checkpoint. Just be sure that it's basically saves some memory, but the idea is that you want to be sure that you can load and offload basically from GPUs to your CPUs or sometimes to your hard drive if something is larger. The next strategy is going to be mixed precision training. The idea of mixed precision training is that, so you all have seen we saw the like a basically quantization idea. So mixed precision training is the types of training where your model by default is going to be in everything is not going to be, the operation happens in float 32, but you want to, as you move forward, to convert it to float 16 and rescale it back constant. So certain operations which are expensive, instead of doing it in float 32, you do it in float 16 by downscaling, and then after you finish, you calculate the errors or like gradient, you do upscaling into float 32 and you continue. So here what you see basically starting from here forward past, you technically float 32, you copy the weights in float FP16, you calculate the loss, float 32, you scale it back propagation. So you should just constantly jumping back and forth between two precision, 16 and 32, by scaling down and upscaling. All right, so that's this idea is called mixed precision training. It's depends on what accelerator you are targeting. You can decide on the precisions that you want to use. And this brings us to zero redundancy optimizer, or basically the deep speed, which is if you ever wondering yourself or trying to test out doing a fine tuning or build a small GPU at home, I highly recommend you to just work with this one. It's pretty straightforward. It has three libraries right now: 01, 02, 03. So 01 basically it shards the optimizer states. So your optimizer at every state basically has some values, like for the gradients, it shards, distribute those. 02, it shards the optimizer state plus the gradient. So now gradients also basically distribute. 03 basically it just does all of this. So that's the main difference. And then basically memory usage without 0, you can see that basically for that data, how much GPU you need. With 0, basically how much GPU you need. So it's pretty optimized for large matrix multiplications and processes like transformers, where you have lots of values that you need to calculate. There's also a video here. I highly recommend you to later just watch that. The next one is offloading a CPU or NVMe. Basically, if I'm not wrong, NVMe is like NVIDIA or something. Basically, what it does, it helps you to offload basically whatever is frequently being used, whatever prompt is frequently being used. You basically offload them between RAM and VRAM to just make some storage. It's useful when GPU memory is inefficient. It works with deep speed and PyTorch FSTP, and basically it's pretty useful. Let's see. Tensor and pipeline parallelism. So tensor parallelism, we already talked about it. Pipeline parallelism, we talked about it, but we haven't seen it. So where is pipeline parallelism? We are far from. Sorry. All right. We're not going to stay on this one anymore. So quantization, we also talked in the previous class. So there are different types of quantization you can do. And we also say that this days we actually do bit quantization also, like 4-bit, 2-bit, a bit quantization. So it's not important. It's just some challenges in data parallelism and the fact that different. So one thing that I think we didn't mention is that if you have two GPUs and these GPUs, they work like this, so they need to communicate the states, right? The gradients and stuff like that. And that itself could create a bottleneck, because not that when you build a pipeline, when you rent GPUs, it's not like you actually get all GPUs the same. You get whatever is available. Maybe 10 of those are going to be 800, and other one's going to be, I don't know, like a T4 and so on. So those types of GPU, they are not going to have the same performance. That means your overall pipeline bottleneck is going to be for the worst GPUs basically that you have, right? It's going to be the bottleneck that you have. So you need to account for something like this, that this GPUs, they don't perform the same, they don't communicate the same. Now, yeah, so that brings to pipeline parallelism. The what you see on top is without pipeline parallelism. So what's happening? So let's say you have a model that you break it down into 4 functions. Function basically 0, 1, 2, 3. Okay, that's for the forward. So during the forward pass, you need to sequentially go through this. Data starts from left, goes to function 0, which is a forward pass 1, or forward pass 0. The output of that goes to the next one, next GPU. The output goes to the next GPU, and so on. When the F3 finished and you want to do back propagation, you start from F3, right? You do a backward pass and going forward. And this is assuming on top you are still doing a parallelism. Like you are doing basically model parallelism. You splitted the model across GPUs, but it's highly inefficient. Why? Because these GPUs, they're just idle. You know, they need to just wait. At every moment, 1 works, 3 doesn't work. The idea of pipeline parallelism is this one. So instead of passing one batch data to function 0, you break that batch into 4 mini batches. So you pass 4 mini batches. Basically, it's kind of like this. You pass first mini batch to device 0. Then, as soon as device 0 finished with that work, it gets the second mini batch. But the first mini batch that device 0 finished goes to the second device, and so on. So by doing so, you're building this basically kind of like a pipeline that a smaller data goes through these GPUs, but the benefit is that now most of the time your GPUs are utilized. So that's the idea of pipeline parallelism, which is technically Same thing that you have seen before, just ensure to has much smaller, like a mini batch, sometimes micro batch data goes to the GPUs. Because you want them to be constantly working rather than working on a larger amount of data. So gpipe is one example of this, which just one example. Deep speed then again is another example for this pipeline parallelism. Torch pipe, not gpipe, or torch gpipe. Torch gpipe. That's also another example of pipeline parallelism. So these are different libraries that you can use depending on what basically package you're interested in. I'm not going to spend on this. All right, the next thing is teacher and student network. And we talked about this in the previous class, that how could we teach, how could we pick a model like this, a large model, and distill the information of this model into a much smaller model that can do the same task. So that's the idea of the knowledge distillation. So in knowledge distillation, basically you have one teacher model, which is a larger model, and you're going to build series of smaller models. Think about what DeepSeek did, right? They work with OpenAI. Basically, they keep calling to OpenAI. They could just get some data to get the result that they want, and they distill those results into smaller expert models, right? So that's the idea of the same thing. So you have this large model, you make call, you get an answer, and you use that answer to build a smaller model. Over time, the smaller models should, if you train them properly, should perform similar to the larger model. So knowledge distillation requires two components: a teacher, which is a pre-trained larger model, and a student model, which is its job is to transfer knowledge. These two models, they don't need to look alike, but they need to be inherently doing the same thing. It's kind of it's the network morphism. That means if it's the first one is classification, the second one should be also classification. It's not a regression. So, and the paper that was published, it's like this algorithm is like a really old. Actually, it's called dark knowledge. The transferring knowledge from a larger model to a smaller model is called dark knowledge. So the way that it works is that so this is a softmax, right? Softmax with a T or like a T value that's similar to a temperature that it stays. The idea is that you have two objective functions. The objective function is going to be kind of like basically the error, like the loss function that the student has by itself without the teacher, and the loss function of the student compared to the teacher. So there are two loss functions, and you combine them some linear combination. So it's like alpha is some parameter that you decide between 0 and 1 that tells you which one you care more for between students loss and the students and teacher loss. So the way that the model being trained is like this. On top, you have the teacher model is pre-trained. So it's a large model that you have trained. You're not training them. You bring the same data, you pass it to the teacher model on top, it gives you an output. So, and you have a softmax with some temperature T. Then you have this student model on the bottom, which is not trained. You want to train it. You give the same data to the student model, it gives you an answer. It hasn't been trained yet, so the answer is garbage. Then the result of the student goes to two softmax. The softmax with temperature 1, a softmax with temperature T. The softmax with temperature 1, which is a generic softmax, it's kind of like it's a sharp value. Like it makes the distribution. So if you have a softmax with temperature 1, if this is the answer, you basically get one of them with a large peak and the other one technically have a smaller peak, something like that. If the temperature is larger, this becomes kind of smoother. Like if this one goes down, the other one comes up. The idea is that when you want definite answer, you want softmax to be like this. When you want a distribution, you want the softmax to give you a smoother curve. So the two softmax that you see the output of the students, the one on the bottom looks like this. Why? Because we want to do classification. We want definite answer. The one above it is the distribution. You get that distribution and you compare it using a Kane divergence with the output of the teacher model. And you want that distribution to be as similar to the distribution of the output of the teacher model. So that basically becomes soft error and hard error. So it's just an example of the model. So you, which one is this? The name of the model is not here, but it had a name. The baseline is 58%, and 10 times ensemble goes to 61%. If you distill it, you get 60%. Much smaller, basically, you get almost as bar performance and better than the baseline also. This is an example of this distillation and especially the distilled bird. So what you see, the bird, so that's the still bird, the bird is over there. 340 number of parameters, you see it's much higher, but typically is much better. So you can distill a large model, transformer-based type of model, into a smaller model, and sometimes you not necessarily always you get a better result. Most of the time you don't get a better result. You get as bar with, but it's also possible. And one other thing that this is also possible is that you can have multiple teachers and distill them all into one. So here the idea is that you have 3 teachers that, let's say they are specialized in 3 different tasks. The job is to do 3 different things. You bring those, and using that, you build this super student. All right, this is like a super student. And from that student, you go build other students, basically. So it's kind of like it's like a two-stage distillation. And the last one is called noisy student. Most of you. But the idea here is that you have a teacher, you label some data, you use that data, you create a student called noisy student, then you use that noisy student, you basically, noisy student, the idea is that you do dropout, stochastic noise and stuff like, you make it noisy during the training, that's the idea. And then you replace the teacher with the noisy student and you repeat the process over and over. So by doing so, you technically you're not using the teacher after the first iteration, you kind of replace it with the noisier version of it. But what you can see here is that on the x-axis, you have number of parameters in millions, and that's the image and accuracy. Noisiest student, as soon as probably like a 13 million parameters, has reached the highest accuracy in compared to the original basically base models. All right, so it's like a feasible process. All right. Let's stop here.